So, questions? I'm here to answer your questions. No questions? See you on Wednesday? What? Maybe.
Well, that's what I wanted. I wanted help with the factoring of like forward things. You know what I'm saying?
No.
That's crazy.
What?
Factoring things with money is crazy.
Do you have an example?
What do you mean, like grouping? Or is that like pulling some numbers?
No, the thing where we did like you double the first number and you find the factor to the first number, go with factor it out.
So, like, the rational zero theorem? So that's like question 2 on. You don't have one of those? So if we look at this example, it's in there. This is one of the nicer examples that you can come across. Why is that? Because if I ask you to list all the possible, why is this example nice?
The negative one.
No. What are you dividing by what? So you're dividing the factors of this number by the factors of this number. Right? So these are your P's and these are your Q's. So P is a prime, that's nice. Q is 1, that's even better. Right, it's P over Q. Right. So the only possible rational zeros are plus or minus 1 and plus or minus 2. Because the factors of 2 are 1 and 2, and that's it. And you're dividing those by 1. But in a hypothetical situation, let's say if the problem was f of x equals 6, x to the 4th, don't care, 12, right? What would be the list of possible rational zeros? So, well, let's just do this. Let's just list p's and q's. P's are 1, 2, 3, 4, 6, 12, right? And q's 1, 2, 3, 6.
And you don't do the ones that double?
Right, you don't need to list the ones that double. So you just list plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, right? So that's just when you're dividing by 1. Now when you start dividing by 2, plus or minus 1/2, right? 1 by 2 is 1/2. 2 by 2 is 1. I don't have to list that. It's there. 3 by 2, so plus or minus 3/2, right? 2 by 2, 4 by 2 is 2. Don't need that. 6 by 2 is 3. don't need that. 12 by 2 is what? 6, don't need that. Now when I start dividing by 3, I get 1/3. So plus or minus 1/3. 2/3. 3 by 3 is 1. 4 by 3 is 4/3. 6 by 3 is 2. Don't need that. 12 by 3 is 4. Don't need that. Right? And divide by 6. Plus or minus 1/6. Right? Yeah. 2 by 6 is 1/3. I already have 1/3. 3 by 6 is 1/2. I already have 1/2. 4 by 6 is 2/3. We already have 2/3. 6 by 6 is 1. We have 1. 12 by 6 is 2. We have 2. So that's the list. So that's a little more dramatic. Okay? But as far as just listing the possible rational zeros, whatever's in the middle doesn't matter. You just take the factors of the constant divided by the factors of the initial, the leading coefficient. Well, it's not even a possible. It's not a possible thing, right? Usually we would just do synthetic division because we know if something is a 0, then the remainder is 0. But 4 is not even on the list, so we don't need to even worry about 4. But how about -2? Yeah, because now -2 is on the list, so it could be one of the zeros. So let's see. So x equals -2. So we put -2 on the outside. On the inside, we put all the coefficients. 1, 2, -2, -3, +2. So we'll do the synthetic division. 1, -2, 0, right? Then 0 again, -2, 4, 1, -2, 0. Oh, look at that, that worked. Yeah. So yes, -2 is one of the zeros.
You can't narrow it down from there.
I mean, from there?
No, from like if it was 6,
There is a way to narrow it down within side of that. It's just it doesn't give you that much of an improvement. Yeah, your book goes into that in the end of that section, but I usually will guide you like that. Yeah. So now what is the next one? X equals 1, right? Is that the question? So x equals 1. So just do the synthetic division. Remember, the trick is to do the synthetic division again on the quotient. Don't go back to the original. Are you hearing me? Do it on the quotient because then it'll result in a quadratic and it should work. So that works as well. Right? So yes. Because you want to answer the last question. Right. Because you can start at the beginning. To answer the question whether 1 is one of the zeros, you can go back to the original. You can say, remember how we said if the sum of all coefficients is 0, then x equals 1 will work. So there are many ways to answer the x equals 1 question. But if you don't divide the quotient, you won't be able to find the rest of the zeros. Why is that? Well, could you repeat your question? You asked me. Yeah, so what's the benefit of dividing the quotient on the second division rather than dividing the original? Yeah, because now this is the quadratic, which you got as a quadratic here. And you can always solve a quadratic. Because your polynomial now is x plus 2, x minus 1, x squared plus x minus 1. That's your polynomial right now. If negative 2 is a 0, x plus 2 is a factor. If 1 is a 0, x minus 1 is a factor. And then that's the quotient, which is a quadratic. You can always solve a quadratic. To find the rest of the zeros, set this to 0 and solve. If you don't divide the quotient in this step, you will not get a quadratic. And if you don't get the quadratic, you won't be able to continue. So you'll still be able to answer part D, but not part E. Okay? Well, now it's just a quadratic formula. You probably can get something imaginary. Well, maybe not. So that's negative 1 plus or minus square root of 5 over 2. So these are the rest of the zeros. Right? So the zeros are negative 2, positive 1, and those two. Now remember how we said all those nasty zeros, irrational and imaginary, they come in pairs. They always have a conjugate pair attached. Who are my online students? Maybe the link doesn't work. Is the link not work? Okay, that's what you just sent me, right? Okay. What are online students? Well, maybe they don't need a review. So that's it. Does that make sense? So just review these concepts. So this type of question you might expect will actually kind of guide you through the.
Well, there's part F.
Well, now we can do part F is easy. Because we need to sketch, right? So the sketch, your intercepts are negative 2, positive 1, right? And those two numbers, you can actually plug them in a calculator to at least approximately see where the intercepts are. So let's say negative 1 minus the square root of 5 divided by 2 is that, negative 1.6-ish. So you know you're going to have an intercept somewhere here. And the other number, negative 1 plus the square root of 5 divided by 2, so 0.6-ish. So you have this intercept. What is the end behavior of this polynomial? Right, just regular parabola. How do you know that? Right, so it's even degree, positive coefficient, so it looks like that. So then you just can connect the dots, right? Doesn't have to be symmetric. No, because all those have single multiplicity. You even know the y-intercept is going to cross the y-axis at 2. Yeah, you just look at the leading term. That's all that matters. Even degree, so that's a parabola, and then plus or minus is positive. So just a... Yeah, the last number is the y-intercept. Yeah, because again, if you just... The y-intercept means x equals 0, so you're just left with the last number. The first question on that list deals with all the multiplicities. The question 1, when you actually have to worry about multiplicities. So f of x is x cubed, x plus 2, x minus 3 squared. So I'm going to make a little table, list of zeros and multiplicities. So what are the zeros of this polynomial? The first one. What's the multiplicity of 0? 3. What else? Negative 2. What's the multiplicity of that? 1. And what else? 3. And the multiplicity of that? 2. What is the degree of this polynomial? 6. So just the sum of all multiplicities, right? So then we know the end behavior. Even degree polynomial, if you FOIL this all out, you're going to end up with x to the power 6 as the first term. So it's going to be positive, right? All x's are positive. So it's going to look like a regular parabola. Right, so because again, you think about the polynomial in the extended form, if you talk about the degree of a polynomial. So the intercepts are 0, negative 2, positive 3. And this is the end behavior, right? Well, now let's connect the dots. So I have to start on the left on top. I have to hit negative 2. What will happen at negative 2? How's the graph gonna, what is the graph gonna do at negative 2? Just gonna go straight through, because the multiplicity it's 1 is gonna look like a linear, basically, function. Just gonna go straight through. Now it has to turn around and hit 0. What's gonna happen at 0? Yeah, it's gonna kind of wiggle through 0, behave like a cubic, right? Then it has to turn around and hit 3. What's gonna happen at 3? Bounce off 3. And it ends up where we expected it to end up. So it's consistent with the end behavior. Right? Yep. This stuff is nice, right? Does that do? Yeah, well, those are rational functions. That's like question number 5. By the way, those questions are clearly not in any order, meaningful order. So those will, yeah. So for question 5, you have 2x squared plus 7x minus 4 over x squared plus x minus 2. You would have to factor top and bottom. Can you? Can you factor the top? I don't. Can I? Yeah, I can. I should be able to. So probably x plus 4. Yeah. X plus 4, 2x minus 1, and the bottom is x plus 2, x minus 1. So it's always helpful if you factor. So x, y intercepts. How do you find x-intercepts of a rational function? The top. Whatever makes zeros of the top are the x-intercepts. So right away, x equals negative 4, x equals 1/2. Whatever makes your numerator equal to 0 would be the... Oh, yeah, it'll be fine. You're not taking this on my math lab. I mean, I'll understand what you mean. Unlike the poor online students. The y-intercept. How do you find the y-intercept? If any. Yeah, you do, of a general function. Set x equal to 0, no matter what function is. You're going to set x equal to 0. So it'll just end up being the ratio of these two numbers, right? If x equals 0, it'll just be negative 4 over negative 2. So it will be the y-intercept. Yeah, y equals 2. And since the last part of this question is to sketch, I can start sketching this. Mike, if you set x equal to 0, you'll be left with this. Negative 4 over negative 2.
Negative 4, and then there wasn't anything on the bottom. Just be no y-intercept.
Yeah, so no y-intercept. So actually the y-axis would be one of the vertical asymptotes.
Then if it was, top number over -2.
So then there's 0. Yeah. So it goes through the origin. So that 0 would be one of the x-intercepts as well. So anyway, so that's 1. So we found that. 2 vertical asymptotes. Now remember, vertical asymptotes are zeros of the denominator after we reduce the fraction. Since it's nothing to reduce, it's just whatever makes denominator equal 0. So what are the vertical asymptotes? Right? But remember how that works? If you cancel something from the denominator, it's no longer a vertical asymptote. It just creates a hole in the graph. But you don't get an asymptote.
Would it be so after you reduce, so would that be from like an x plus 2 on top?
Yeah, so if you reduce x plus 2,
I know, it's just
so yeah, so x negative 2 will no longer be an asymptote, but you'll just have a hole at negative 2 in the graph. Okay, horizontal asymptote, if any. Do we have a horizontal asymptote here? What is it? 2. Now, how do we know that? Right, so you look at the degrees. If the degree of the numerator is the same as the degree of the denominator, then it's just the ratio of leading coefficients, 2 over 1. Okay? Now remember, if the numerator is less, then the asymptote is 0. If the numerator is greater, you don't have a horizontal asymptote. So if you have a horizontal asymptote, the next question was to find the oblique asymptotes. Well, you cannot have both. It's either one. If you have a horizontal asymptote, there's no oblique asymptote. When does the oblique asymptote happen? How do we know that? How do we know whether a function will have an oblique asymptote? It's greater by 1. So let's say if the numerator was a cubic, then yes, it would have an oblique.
so f plus plus.
Right, you cannot have both. But you can have neither. You know, if you have a 5th degree over 2nd degree, then it's neither horizontal nor oblique. But the oblique happens only when the numerator is greater by 1, and the way we find it, we actually divide top by the bottom, and we take the quotient. So it's always going to come out linear. All right. Yeah. No. In the case, if this was our problem, 2x cubed plus 7x minus 4 divided by this, if this was our problem, you would still have the same vertical asymptotes. You would change the x-intercepts dramatically, right? But you would not have a horizontal asymptote in this case, because the numerator is greater, the things will go to infinity. But you would have the oblique asymptote, and to find the oblique asymptote, you would actually have to divide. So you have to perform the long division here. And you have to be very careful because we're missing a square in our numerator. But the way we do the long division, we would divide the first 2, right? So 2x cubed divided by x squared is what? 2x. 2x, right? Then we'll multiply back. So that'll give us 2x cubed. So you see, I should have put a 0 in here because I'm getting a square term plus 2x squared minus 4x. So when I subtract, 2x cubed cancels with 2x cubed. Since there is no square term, it's really a 0x squared. I'll end up with negative 2x squared. And then 7 minus negative 4 is 11x. Yeah, that won't matter. But right, you take negative 4 down, and then you repeat the process. Negative 2x squared divided by x squared is what? Negative 2. And you can stop, because this is your oblique asymptote right there. Whatever the quotient is your oblique asymptote. So you don't need the remainder, none of that junk. The second you got your linear mx plus b, that's the oblique asymptote. So the y-intercept is negative 2, and the slope is positive 2. So that's the oblique.
The denominator is greater or equal to the ratio of leading coefficient.
No, only if they're equal, then it's the ratio leading coefficient. If the denominator is greater, then the horizontal asymptote is 0, is the x-axis. Because the denominator will overpower the numerator.
So the y-intercept is 2 and the horizontal asymptote is 2?
Because now remember, it's okay to cross the horizontal asymptote for small numbers. The horizontal asymptote really kicks in for large numbers of x, and it's still okay to cross it. While the vertical ones, those are out of limits. Okay? Because really we can cross the horizontal, no problems. And we will test whether we cross the horizontal asymptote, and we know we will. That's the y-intercept. But anyways, if I actually now, I can sketch the graph of this thing. So let's label everything. X-intercept, -4, +1/2. Y-intercept is, well, let's call this a 2, right? And what else? The vertical asymptotes are at -2 and +1, and horizontal asymptote right? So we have enough to actually connect the dots. There's nothing else we need to do to graph this. Because if I look in this region to the left, I need that x-intercept, and I have asymptotes. So how do I graph? So it's this thing, right?
And how do you know whether it's like switches or stays on the same side?
The multiplicities. That's the big thing. If, when in doubt, use the multiplicity, because everything has a multiplicity of 1 right now. So the signs, you see the sign changes. Yeah, but you see, I don't even need it here. Look at the middle. The only way to connect this is probably to do something like that. Right? And the only option on the right is that, because I don't have any more x-intercepts. I cannot go on the bottom. Because if I go on the bottom, I'll hit the x-axis again, and there are no intercepts. Or you can use that multiplicity interpretation. So the sign changes at every x-intercept. You see it went from plus to a minus. At the asymptote, went from a minus to a plus. At the x-intercept, went from plus to a minus. And again, at the asymptote, went from a minus to a plus. So the sign changed at every dramatic event, like the x-intercept and the vertical asymptotes, because all of those had single multiplicities.
That's if it's
Odd, right? Well, good. We just kind of did whole chapter 4, basically, in that. That was the entire chapter 4, really. We almost checked all the little theories in there.
Sam Green.
Chapter 5. No, of course. Oh, I forgot to turn the mic on. So, well, it's just when in doubt, if you want to know what happens, whether you're below or above the x-axis. But it just works same for the polynomials. The odd multiplicities have opposite signs. So the sign changes at odd multiplicities. Okay. What?
To determine if it has an inverse function, the only thing you have to do is just try it, right?
No, you have a 4-step process of finding the inverse of a function.
Like, but okay, so
Yeah, and that's it. Yeah. So you should come up with the inverse there if your function is x to the 7th plus 9. After you do your process, you're going to end up with the 7th root of x minus 9, something like that. Well, you switch x's and y's, and then you solve for y. So you have to subtract 9 and then take the 7th root.
How do you, so for number 3,
Mm-hmm.
show the 3 versus you just do that for both of them?
Well, that will be too much work. You can, that will be too much work. What you want to do for question 3 is to do the composition. Because what happens if you take a composition of a function with its inverse?
Oh, you get x?
You get x. So that's what you want to do. You want to take the composition in both ways, and you want to get x in both ways. So if your one function is 6x minus 1, and the other function is x plus 1 over 6, you want to do the composition both ways. And if you get x in both cases, then the answer is, well, yeah, those two functions are inverses. So that's the big property of compositions. The composition of inverse functions always results in x.
So with all these on the second page,
Mm-hmm.
like the fractions, would you, like, number 5, would you turn it into 3s and negative?
Yeah. So number 5, definitely you want to, so you have 1/3 to the power 7x minus 1 equals 27. This is the problem where you can get them to, same base, right? So yeah, you will turn this one to 3 to the negative first power still raised to 7x minus 1, while the other one is 3 cubed. Right, so then by the rules of exponents, it tells you when you raise power to a power, you multiply them, so you get 3 to the negative 7x plus 1 equals 3 cubed. And now you can just set exponents equal to each other. So that's the big property. If the bases are the same, then exponents are the same. So negative 7x plus 1 equals 3, and then you just solve for x. So it looks like x is, what, 2/7, negative 2/7? I think.
How do you do, like, 9 and 10 on that page?
So for this question, it's asking you to find the x-intercept. And the function is 5 plus log base 3 of x. For any function, how do you find x-intercept? Hmm? Set y equal to 0. Regardless of a function, set y equal to 0 and solve for x. So your equation is 5 plus log base 3 of x equals 0. Right? Well, how would we solve that?
Subtract.
Okay. Subtract 5 from both sides. So you have log base 3 of x equals negative 5. And how do you solve for x? Right. So you just rewrite this in exponential form. Base raised to negative 5 equals what's on the inside. So x equals 3 to the negative 5th power. So we're done. So whatever that is, that's a small number right? It's 1 over 3 to the 5th. That's a tiny little number. And then 3 to the power 5 is 243. Yeah. And 1 over that is very small. But well, let's finish with that. Are we done with that? Yeah? Well, let's talk about vertical asymptote. What is the vertical asymptote of a logarithmic function? Of a very basic logarithmic function? 0, right? So the y-axis is the vertical asymptote, right? The logarithmic function dives at the y-axis. Okay, well now if you look at question 10, you have 2 plus log of x plus 1. Think about the shifts. How are you going to shift the graph of log of x to get that function? Right, so you're going to shift 1 to the left, right? So that will shift the vertical asymptote. So 0 will go 1 to the left. So yeah, so negative 1 in that case. So in question 10, yeah. So we know that shifts 1 unit to the left. So therefore, the vertical asymptote is x equals negative 1, because x equals 0 shifted 1 to the left, right? The graph of this function would be, this is the original log, right? Well, now you're shifting it 1 unit to the left, so it becomes this. The fact that you're going to shift it 2 units up will not affect the vertical asymptote. I hope that makes sense. Does that make sense? Okay. Hmm? Sure, you can give me a problem from our quiz today. That's okay. Are you sure you're saying it right? So log of 6x like that? Okay. 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 Like that? So you have 2 logs equals a number. You don't like that. You want to have 1 log equals a number. Can we fix that? How? Yeah, so this turns into division. Log of 6x plus 5 over x minus 1 equals 1. Right? So now what? Hmm? No, the other way around. 10 to the first power. Yeah, so this is base 10. So it's the base to that power equals what's on the inside. So it's the base 10 to that power equals 6x plus 5 over x minus 1. Yeah, exponential form. That's the easiest way to do it. So then just solve that equation. Multiply both sides by the denominator, so 6x plus 5 equals 10x minus 10. And then you just solve that. Right? Just multiply by x minus 1 and then solve. Now you have to make sure, well, let me actually finish this. So subtract 5, subtract 10x, so it's negative 4x equals negative 15, so x is 15 fourths, right? We have to make sure that 15 fourths does not turn any insides into a negative number, right? So 15 fourths is positive, so it works in the first log, still positive. And 15 fourths is greater than 1, so it works in the second log, still positive. So you just kind of want to double check. If the answer was 1/4, for example, it wouldn't have worked on the second logarithm, because if x is 1/4, you're going to get something negative on the inside, and that's not good. Well, it has to work for both. Yeah, if it does not work for just one, then it just doesn't work, period. What? So that one we need to break up into many little. So question 20, natural log of x squared over y. So we need to split it up, right? So what do we notice? What is the big thing here? How do we start? Yeah, you see it's a natural log of a division. So division turns into subtraction, right? That's what you're asked to do. Is a sum, difference, and or constant multiple. So are we done? No. Well, I want to get rid of that power, yeah. Drop the 2 down. So now we're done. Yeah.
For 23, are you changing the same thing?
Yeah, you can. For 23, you can. So you're going to go for base 5. So your probably answer is going to be negative 3. Right?
Would be negative 3?
Mm-hmm. Right, so now you're going back to the single logarithm. Which question? Yeah. So we're going to the single logarithm. Right, so first, order of operations, parentheses first, so it becomes 7 log of x over y. The division, I'm sorry, subtraction turned to division. What do you do about that 7? Yeah. So it's the entire x over y raised to the power of 7. Yeah. Well, here you just have to use the properties. Log base 8 over square root of 8. Right? You don't need a calculator there. See, the numbers match. You just have to think about the square root as something else. What operation is equivalent to taking a square root? No, that's the complete opposite. What's the equivalent?
No,
One half. So this is the same as log base 8 of 8. Log base 8 of 8 to the power 1 half. So if you think about all your square roots like that, then what is the answer? 1 half. Yeah, we learned that a while ago. I don't think I'll ask you that, but still. Yeah, so the formula for the compound interest formula. So it's the principal 1 plus rate over n to the power nt, where n is the number of times the interest is being compounded. So when it says compounded annually, for number 27, when it says annually, that means once per year. That means n equals 1. You only do it once per year. So here, all we know now that the rate equals 6%, we need to find the doubling time. The time it takes for the investment to double. Now, if this was a continuous situation, then remember the relationship between the rate and the time it takes to double. It's a natural log of 2 divided by rate or whatever. But it doesn't work here, because it's not that continuous thing. So right now our model is the principal times 1 plus 0.06 to the power t, right? N equals 1. So it's really this. This is our model right now. Right, but does it matter? We're looking for time it takes to double. Remember how we talked about it, that the doubling time is independent of the initial investment. Because if your initial investment is P and you want it to double to P, right? Whatever you start with, it will double. So when you divide both sides by P, the equation becomes 2 equals 1.06 to the power T. Okay? Well, now how would we solve that equation? Now we need to solve for t. Whatever we find for t will be the doubling time. What? Sure, so log, natural log, doesn't matter. I like natural logs. So what that does, it brings t down. So then t equals ln of 2 over ln of 1.06. And I can plug that in my calculator. It will tell me the time it takes to double. Well, we got lucky. N equaled 1. If n was something else, it would be a little different. So about 11.9 years or so. Almost 12 years. How do we do 28? We know that it took to go from 3.9 grams to 0.8 grams in 70 hours. That's what's given. Find the half-life. That's 28. So it took 70 hours to decay from 3.9 grams to 0.8 grams. So find the half-life. Right. And why do you say that? Yeah, but what are you going to do with that rate? Yeah, because we know the half-life is natural log of 2 divided by rate. So the second I find rate, I have the half-life. So I can set this up, right? This is the decay model, right? This is the amount equals the initial amount e to the negative kt. So I know in 70 hours, 3.9 grams will become 0.8 grams, right? This is the initial amount, 3.9 grams, that's the future amount, and it took 70 hours to get there. So solve for k. So how do we solve that? Well, before, yeah, you have to get rid of the constant, divide by 3.9. So e to the power negative k times 70 equals 0.8 over 3.9. Now take natural log of both sides. So it becomes negative 70k equals natural log of 0.8 over 3.9, right? And then divide by negative 70, so k equals natural log of 0.8 over 3.9 over negative 70, right? So that's the rate. Shouldn't be negative. The rate should come out positive. Mm-hmm. Mm-hmm. By negative 70. So whatever that is, natural log of 2 divided by that will be the half-life.
So for number 26, is it just the ln of 2 over 0.05?
Yeah, so we see that $5,000 doesn't matter. Yeah. So I can just take whatever this number is, you know, since doubling time, I'm sorry, half-life is ln of 2 over k. And if that's k, so then it'll be ln of 2 times negative 70 over ln of 0.8 over 3.9. So I can plug that in my calculator. So I don't have to carry the decimals. So natural log of 2 times. Well, because I'm dividing by this, the same as multiplying by the reciprocal. Divided by, all right, I'll go backwards. I'll go from the denominator. So it's easier. So that's my denominator. Bam, times negative 70 times natural log of 2. So I got 30.6-ish hours. It doesn't seem right.
Wait, what did you have?
Is that what you got? Oh. Why did I say it doesn't feel right?
And then for 26, we got 13.8.
Maybe, yeah. I don't know, but that feels good. Easy stuff. Other questions?
It's gonna be this short.
I don't know. Do you think that was short?
Yes. I mean, really long. I'm not big.
And of course, review your quizzes. Quizzes 5 through 9. It's not just that. This is just to give you a little bit of a taste. Right? Because I might have left some questions out. How does this thing work? I should be able to draw a circle. But I don't know how. Oh, just weird. So again, this is, we can play with the bases here. So you just want to just simplify the expression log base 3 of 1/9 to the power 3. Because the simplifications will work really well if the bases match, right? So think about 1/9 turning into base 3. 3 to what power equals 1/9? -2. So this is the same as log base 3. I mean, there are many ways of doing this problem. I mean, yeah, you can just bring 3 down and you say it's log base 3 of 1/9, and then you just told me that it's -2. To what power you raise 3 to get 1/9 is -2, so it's just -6. That's even easier. Yeah, you can. No, you could have done it this way. No, it's still going to be -6. So it's log base 3 of 3 to -6. So it's still -6. The top way is easier. Bring the power down and then you actually get the value for the log. well, what is the change of base formula? In general, if you have log base a of x, what is that equal to? Where b is whatever you like. So now if I give you log base 5 of 33 and I'm asking you to express it in terms of natural logs, so I'm just asking you to change it to base e, right? Change log base 5 to natural log. So if using that formula, what would that be in terms of natural logs? ln of 33 over ln of 5. Okay? And that's it. No. It's ln of 33 over... Yeah, well, I wasn't even asking you to compute it, right? The question was, we write in terms of natural logs. On 16, you actually have to compute it. Because that's what I asked. Didn't I? But that other one, that log base 7 of 798, and I'm asking you 3 decimals. So here you can do ln, you can do log, doesn't matter. You can do log of 798 over log of 7 and plug that in your calculator. 798 log divided by, so 3.434, 3.434, rounded to 3 decimals. Yeah, no, e to the 3. Yeah. Well, your equation is natural log of x equals natural log of e cubed. So the insides have to be the same. So x equals e cubed. I mean, you're right. I mean, this is natural log of x equals 3. To solve for x, x has to be e cubed. But it's just easier to see if the logs are the same, then the insides have to be the same. So x equals e cubed. What? Yeah. This is a nice one. So ln of x squared equals 3. So we have a single log equals a constant. So how do we solve that? Hmm? Yeah, you write an exponential because these are your rules, right? If it's a natural, if it's a log equals a number, then we write it in exponential. So what would that be? What is the base? Yeah. So x squared equals e cubed. Yeah. So what is... Right. But if you take the square root, right? So x is plus or minus e to the 3/2. If you bring the 2 down first, you will lose the negative solution. You can do it in your calculator, whatever e to that power. 3/2 is 1.5, e to that power is that. Yeah, so it's plus or minus that. Because look, even if I graph this function natural log of x squared, I'll get two solutions out of that. If I do natural log of x to the power 2, and this one is 3, so I'm getting two solutions, negative 4.48 and positive 4.48.
Do you have that in front of you?
What? The what? Kind of, yeah.
Number 7. I'm negative 2 log 5 equals log of 1 minus log of 5. Log of 1.
No. I want the answer to number 7 look like the question 6.
But it's the opposite question.
Right. So the answer should look like the actual question in 6. So it should be log some base of something equals something.
Log of 1 over 25. Don't want it.
No, I don't want it to split out. I want it to say, okay, it's log base 5 of 1/25 equals negative 2. Right? Mm-hmm. Is that okay?